Oh, hello everyone. Welcome back to another Learning Glass session. Today we'll talk about the first law of thermodynamics and how we use heat capacities or specific heats. Well, same thing, just different units. One is intensive, one is extensive. But the specific heats are just ways to model what the internal energy changes or the enthalpy changes. The name is unfortunate, specific heats. What it really should be considered as the response of the internal energy to temperature or the response of enthalpy to temperature. And it depends on your system because your system is made out of different molecules. Depending on whether you're working with air, water, or a mixture, the heat capacity will change because the molecules respond, the relationship between energy and temperature. So it's really energy, but the temperature is the feedback we get. It's the thing we can actually measure. So we developed this thing, thankfully very useful, called specific heat to relate internal energy to temperature and enthalpy to temperature. It doesn't directly relate to heat. You can use specific heat without heat transfer. Adiabatic system, you can still use specific heat. With change in pressure, you can still use CP. Change in volume, you can still use CV. The name is unfortunate, but nonetheless, it's still very useful. So, where is it? For any process, actually, let me change the name of this thing too. Thermodynamics and specific heats, let's call it internal energies and specific heats. Got my notes mixed up there. It could be called what we're going to, like I was just saying, specific heats give you the response of energy, specifically internal energy, and depending on whether we are working with an open system or a closed system or chemical reactions, we will use enthalpy instead of internal energies. So the way that these should be thought of and used is that for any process, no matter if there's heat transfer or not, whether there's volume change or not, whether there's pressure change or not, this is how you should use specific heat, CPs and CVs, where if you need to find delta U, you can relate that to CV dt from some initial temperature to some final temperature, and similarly, if you need to find delta H in any process, you can relate that to CP dt, where in real life, the heat capacity changes with temperature. It increases with temperature. And it doesn't matter if the volume changes or not, doesn't matter if the pressure changes or not, doesn't matter if there's heat transfer or not, this relationship still holds. That's how you use these. Okay. So, specific heat gives the connection, let's say connection between energy and temperature. And so here, this internal energy change, the energy of the molecules changes with temperature, and that proportion is the CV. Enthalpy change depends on the temperature change, and that proportion depends on Cp. And that response between temperature and energy depends on the molecule. Depends on molecule structure. So one trend is that the more bonds your molecule has, the bigger it is, the more bonds it has, the more energy it can take without temperature change. So for the same amount of energy in or out, the temperature changes less, because those bonds can have degrees, those bonds can accommodate that energy. So it depends, that's why these are different, because these molecules are different for each system. And it could be a mixture, which is an average of all those different molecules in the mixture, and it increases with temperature. So the higher the system temperature is, the more heat capacity it has, the more specific heat it has. And one system we're going to work with a lot in thermal fluids is air. So ideal gas, air, specific heat. We're going to chart this in terms of kilojoules per kilogram Kelvin. This is grams, this is Kelvin. Kilojoules per kilogram Kelvin. We can plot this relationship with temperature of specific heat. And it's in the range of 0.7 to about 1.2. So let's say 8, 9, 10, 11. 8, 9, 10, 11-ish. It's a little bit, put this one. These two are a little off. Something like that-ish. 8, 9. Okay, something like that. And for ideal gas, it's simpler because it only depends on temperature. That's one simplification. That's the main simplification of using the ideal gas assumption. And from 1800 Kelvin to 300 Kelvin, the Cp starts at about 1, a little bit over 1. Then it ends up at over 2, 1.2. That's how this heat capacity changes with temperature. Then the CV starts at 0.7-ish, a little bit above. It also goes up with this same trajectory. Why? Because under the ideal gas assumptions, you can simplify this relationship using the first and second laws that Cp equals Cv plus R. So what that means is that the difference here is R. It's just simply a translation by R. And this is in the units of kilograms, so R is not the universal gas constant, it's the gas constant for air. And so this changes significantly. So if I were to compare the Cp value at 300 Kelvin to the Cp value at 1800 Kelvin, that's here, and then 300 Kelvin, this would give a 24% increase This is the difference of 24% here. So that's a big change. So not accounting, if you were to have a system undergo a process where the temperature increases from 300 to 1800 Kelvin, the heat capacity would change by 24%. So this integral would become more important to capture this temperature effect. How do you capture this temperature effect? You have to somehow find a function of heat capacity with temperature, or you can look up tables to find the enthalpy at 1800 Kelvin and the enthalpy of 300 Kelvin. That will give you, if you analyze the table correctly, which takes some skill, for like if you're in steam tables, it may depend on other factors. But for ideal gas air, the enthalpy only depends on temperature. So you can find the enthalpy on an ideal gas air table and get that directly. Or if you want to use an equation, which sometimes is more convenient, like for codes of automating this, or developing a code where you can change the temperature and things like that, and do this energy balance using conservation of energy and first law. An equation would be more convenient. You would use something like this. Then the next question is, how do you capture this temperature effect? Well, what NASA does is they use a polynomial. A polynomial with like seven terms, and they fit the data that they have done, that's been worked on over the years for many different molecules. It depends on the molecule. So NASA, when they do their rocket science, they burn fuel, they go to high temperature, they produce all of these different molecules depending on the fuel and the oxidizer and the conditions. So they need to know all the molecules depending on how accurate they need to be. And they make a polynomial fit. So in our tables that we have posted on Canvas, we have a simpler version of this, where it's the heat capacity in the per mole is an ideal gas polynomial. So it's assuming it's ideal gas. NASA also does that for many of their calculations, and it's a pretty good, unless you go to really high pressures, which you need to be more careful at really high pressures, and high temperatures in some cases. But for our cases, we can use this ideal gas polynomial. In table A2, they have coefficients for different molecules. So each molecule will have A, B, C, and D with these either linear, squared, or cubed, and then a constant for Cp. So this would be kilojoules per kilomole per Kelvin. So this is in terms of moles units. And this for air. You can read these coefficients off of this table and it will give you this curve here. Okay, so if you needed to find delta H, it doesn't depend on, you can find delta H as long as you know Cp and the temperature interval you're interested in. So you can use this to find delta H. It doesn't matter if pressure changed or not. It doesn't matter if there's heat or not. You can still find delta H. If there's a temperature change, there's a delta H change, no matter what else happens in that process. You can always use this relationship. So doing that, we can use this polynomial, and in a lot of mechanical applications, we work in the mass units, so you can use this but convert to per mass by saying delta H equals delta H per mole, that's what this bar is, over the molecular weight. So this is converting moles to mass. By dividing by molecular weight, you go from moles to mass, and that would be the integral of this polynomial. So at the end, you should get this divided by molecular weight, but this polynomial would be the integral of A as with t, that would be AT. The integral of BT is 1/2 BT squared. The integral of CT squared is 1/3 CT third. The integral of DT third is 1/4 DT fourth. So that's the benefit of using this polynomial, is that you can add a lot of terms. The more terms you add, the more accurate you can fit this experiment. And depending on if it's a polynomial or other, like NASA also uses it as a natural log term, or a 1/t term, which gives you natural log in the integral. That's how they get even more accurate, but this is still pretty accurate because it does capture most of this change with temperature over a relatively big range. And this would be the polynomial in our book, in our tables. It's less accurate than NASA, but it's pretty good. And for a given temperature range, you would evaluate this at T2 and T1. And the molecular weight here would be able to convert this molar trend into mass per mass trend. Okay, so let's apply this for heating cases. So so before we do that, let's get reminded where in some cases, when we're applying the first law to the analysis, we use either internal energy U or enthalpy H. When we need to use internal energy U, and the best thing to remember is use internal energy U if you have a closed system with no chemical reactions. Use delta U to capture the internal energies of your system, the change in internal energy. If you have a closed system with chemical reactions, even though the system is closed, there's no mass coming in and out, instead of using internal energies, you use enthalpy to capture internal energy, because the chemical reaction can cause some PV effects which are captured with enthalpy. So closed system with chemical reactions, you use enthalpy change, because that's a way to capture internal energy with this extra PV term. And you could, all the tables are, in terms of chemical effects, are formulated at enthalpy, because you need to capture this PV term due to the chemical reaction, which is a factor. Even though the volume doesn't change, the pressure might change. That's why you need enthalpy. Okay, so for CV, you can use, for ideal gas process, you can use this relationship here to convert what the table only gives you CP. It does not give you CV. So you have to remember your theory, for ideal gas, CP is related to CV with this relationship here. So if you were to apply that, you would say delta U equals delta U molar over the molecular weight. Then you would say, okay, this would be also related to an integral, but with CV, the molar CV that we can get from the table indirectly from this. So if we remember that for ideal gas, this would be the integral of Cp minus R. That's how you would connect. This is the universal gas constant because we're in molar form, you're in universal. So the tables only give you heat capacity Cp. Why? Because if it's an ideal gas table, then you could always relate Cp to Cv using the universal gas constant in molar form, and then we convert to mass using the molecular weight. So that would give you, let's see where I can fit this in. So let me just rewrite this here. So delta U is, in terms of mass, related to, you can convert using molecular weight, and then you can find this from the Cp that changes and a constant, universal gas constant. So that integral would be the integral of Cp minus R. So if you're to remember our rules of arithmetic, if you have this function of t here and you subtract the constant from that, it's, you cannot subtract R from t directly. That won't affect this term. This constant won't affect this term. It won't affect this term. It'll only affect this term. So it'll look like an integral of A minus the universal gas constant. Then everything else is the same in the integral. And then this integral will be shifted by this RU term here after you do the integration. Okay, so by the ideal gas, you just have this shift by the gas constant, where if you're in mass, you use air gas constant. If you're in moles, you use the universal gas constant. And this molecular weight, I should have added this here, is how you convert from these molar parameters given in the table to mass. Okay? So let's apply this to a simple heating case where the system is closed without chemical reactions. So closed system means internal energy change if there is no chemical reactions. So in the first law for this case, we're going to use the change internal energy is balanced by Q minus W. That's how the first law would look in this case. So we can look at a table to say that if we know some heat transfer, if we know that, if we're given that, or somehow we can measure that heat transfer, that should balance out with the energy change of the system, the internal energy change. So let's say we have a box, rigid box, the volume does not change. Then simple heating, some amount of heat transfer comes in. And you go from T1 equals 300 Kelvin, it's ideal gas air, T2 equals 1800 Kelvin. It's a rigid box, so there's no volume change. So the first law for that case would be delta U, there's no chemical reaction, there's no mass coming in and out, so you can keep track of the system molecule energy with delta U equals Q minus W. Here the volume doesn't change, the boundaries don't move, so there's no mechanical work. And there's no flow, so you don't need enthalpy. There's no chemical reaction, so you don't need enthalpy. So here you would have the first law amounting to the heat transfer equals the change in internal energy. Well, so if we know the temperature change, we can either look up the table in the ideal gas air table to find the internal energy change between 1800 Kelvin and 300 Kelvin. So for each temperature, there's a given internal energy. So at 1800 Kelvin, the internal energy can be found on a table. At 300 Kelvin, the internal energy can be found on a table. But if you're using equations and some automated or some computational code, you would use heat capacity to capture this internal energy change with temperature. And the table will give you an accurate result, and the better your curve fit, the more detailed this equation is, the closer it is to experiments in tables. So what we do is we use this concept of CV giving you internal energy. CV does not give you heat. CV gives you internal energy change with temperature. That's the theory, that's the concept. Don't connect this to heat. There might be some work term there. So it depends, it's more direct connection to internal energy there. Okay? So we will need to find internal energy. So the internal energy of air in this case is molecular weight to convert this polynomial. What we're going to get is we need to find this integral, so that would be this coefficient in the table shifted by the universal gas constant, because this is moles, and CV equals Cp minus R, and that's how that changes this equation here. Then the integral will give you a T plus 1/2 B T squared plus 1/3 C T third plus 1/4 D T fourth, evaluated at 1800 Kelvin and 300 Kelvin. So that would give you delta U of air equals, let's say, 1/29 . That is the molecular weight, it's 29-ish. Molecular weight there, divided by molecular weight, so it's kilograms at the bottom. Then this would be A, I didn't write down A, it depends on the molecule, so you can look up that table for air. Air is not a molecule, it's a mixture, but you can still define it. It still has these average molecular weight, still has these average properties for a given defined mixture. And the universal gas constant is 3.14, that's universal, times 1800 Kelvin plus 1/2 B times 1800 Kelvin squared plus 1/3 C 1800 Kelvin cubed plus 1/4 1800 Kelvin to the fourth minus A minus 8.314, that's the universal gas constant, times 300 squared plus 1/2 B 300, no, that's not squared, it's just linear, sorry. The next one is squared. C here's cubed plus 1/4 300 to the 4th. So this would give you the integral of CV dt, which is related to this polynomial given in the table, shifted by universal gas constant for moles or gas constant for air. And by doing this integral, we capture this temperature effect, this function of the heat capacity over this temperature range. That will be more accurate by doing these integral of this polynomial function. And if you do that, you should get that delta U equals 1281 kilojoules per kilogram of air. And so that's the internal energy change. CV gives you internal energy change. And in this specific case, the first law gives you that internal energy change balances with Q. That's the connection. It's indirect. You shouldn't think that heat capacity always has to include heat. Heat capacity can be used with heat. In this case, it just happened to work that way. But that's not the general case. You should just connect it to internal energy, CV. Okay, so this is with temperature effect. So it should be capturing this, what truly happens in real life. It increases by somewhere around over 20% in that temperature range, so this captures it. So that's good. So you can take other assumptions. In some cases in class, we have taken more simpler assumptions. One of those is that if you were to use, let's say we were using, in this same case, we're making a simpler assumption to say, now assume CV is constant. So when you do that, you can either say, you have to pick a value. So let's say that CV is CV average, which equals CV at 1800 plus CV at 300 divided by 2. That would be capturing the fact that it's different at 300 and it's different at 1800, so we're just simply finding the middle ground here. Yeah, like here, here. So somewhere, it's maybe off the scale, but the point is it's going to consider this value, and pick the midpoint from there. So that would give you delta U equals, pulling from this table here, this is this chart. At the high temperature, it's 0.952. At 300, it's 0.718. Then you take a constant average value, and then it'll be and then just this integral becomes simpler. It's just dt. So this would be, let me do this over here, bigger. So if you do that, delta U air would be CV average delta T. And then plugging in the numbers, counting for this average here. 0.952 plus 0.718 divided by 2. This is the constant value we're choosing. And then that just becomes multiplied by the temperature change, delta T. And when you do that, you get 1253 kilojoules per Kelvin, kilojoules per kilogram, delta U air, CV average. So this one is different, not too different, but it's different. But what we've done was simplify the calculation because we're only keeping a constant value, and it does capture the fact that it changes, but it doesn't track it accurately across the whole range. It just picks some value in between. Simplifies the mass, but it changes the value, and we can assume that if we did it right, this is more accurate because it captures the curve more closely. Okay, another one we can take is that. Let's do it up here. Another assumption is now use cold air standard assumption, which is useful but inaccurate, because for cold air standard assumption you also pick a constant value, but you just pick this 300, which is very inaccurate because we apply cold air standard assumption to internal reciprocating engines for Otto cycle and diesel cycle, and also Brayton cycle open systems. Those get really hot from combustion. And if they get really hot from combustion, there's a big change. So let's show the effect of the cold air standard assumption, which is using CV at 300 Kelvin. That is 0.718 kilojoules per kilogram Kelvin. In that case, delta U air equals 0.718 kilojoules per kilogram Kelvin times delta T. It's the same here, minus 300 Kelvin. That will give you 1077 kilojoules per kilogram. And again, this is by the first law equal to Q, but my point is here that you're getting different answers for the internal energy change, which is what CV gives you, depending on the assumptions. So I'll summarize this soon, where in real life, this heat capacity increases with temperature with this certain curve function, and then we can capture and fit this to different molecules using this polynomial. NASA uses more accuracy, and NASA goes to high temperature, so they need to capture this accurately, and they use more terms and different intervals of the ranges and things like that. This is what we have in our book in table A2. Okay, so we see here, I'll bring these back again, but what we've seen so far, that for a simple heating process in a closed system, going with the big temperature range, you'll get a much different result depending on how accurately you keep track of these temperature function of heat capacities. In this case, we use it to find internal energy. But next, what we'll do is analyze simple heating for a flowing system. And for flow open system, you have to use enthalpy to keep track of the internal energy change. And we'll show how different, again, your answer can be of this simple heating system. If you know the temperature change, that constrains the internal energy change, and that constrains the enthalpy change. And that will give you a model for what you can interpret the heat transfer to be. And that interpretation can be flawed depending on how accurately you keep track of this temperature effect. Okay? So this next system will be a open system of air with simple heating. So it'd be a similar first law, except that we use enthalpy change to capture the internal energy change, because the flow has this extra PV term we can keep track of with enthalpy. And internal energy, it's still there, but we use enthalpy to capture it better, more conveniently, and a better way to formulate it. And we should just keep that in mind, that enthalpy is the same thing as internal energy. It just gives you these extra terms to account for more physics that are happening in different processes. Okay, so now simple heating of air in a flowing system. So the air is the system, and it's coming in and out of this box. So let's say we have this box, but it has channels. For the air to come in, air to come out. So this is air, steady flow, steady mass flow rate. So let's say it's coming in at flow rate. The energy, the enthalpy of the flow coming in corresponds to a temperature of 300 Kelvin. The enthalpy after heating, there's energy flowing in from that surroundings into the system here with some quantity Q, and that causes the air to come out at 1800 Kelvin. So again, the first law for this open, simple heating system would be that delta H equals Q minus W, where there's no moving boundaries, so there's no blades putting work on this or taking work out, and there is no moving boundaries, but there is flow, so we use delta H to quantify for that. So, and if this is M1 equals the same M flowing in as the same M flowing out, we can cancel out this, so if you wanted to account for this mass flow rate, you said M delta H equals Q minus W. Here there's no work, so this cancels out. Then if we bring mass flow rate here, we'll get delta H equals Q, because the mass flow rate seconds cancels out this power here, giving you this intensive variables. So if we were to use the table for the T temperature effect, we would get delta H equals the integral from 300 to 1800 of CPT, and then correct for molecular weight, dt, using these fitted values. If we were to plug all that in, we would get enthalpy change, which is what CP gives you, enthalpy change. We would get 1713 kilojoules per Kelvin. So again, this number is different than delta U because delta U is shifted by universal gas constant in this integral. So we will just use this function, integrate that, you should get this number, delta H, and by the first law that equals Q. Then, using constant CP average, you would get delta H equals CP average delta T. And if you do that, you would get 1686 kilojoules per kilogram. That's delta H and that's Q in this problem. Under different assumptions, it's different, which we can assume is less accurate than this because if we capture this temperature effect accurately, it'll be more accurate enthalpy change. Then, using cold air standard, CP at 300, that'll be similar to this equation but with a different coefficient. That will give you a different number of 1512 kilojoules per kilogram. That'll be delta H. So we get three different numbers because we have three different assumptions which are three different levels of accuracy. And so if in real life we know it's experimentally measured, you have to apply a lot of theory to guess this beforehand. What we did before is just to simply get a careful experiment to measure these temperature effects and fit the data to get CPs. And if we capture that temperature effect accurately, this would be the most accurate one. And of course, NASA uses more terms, and they're even more accurate if they use more terms on the polynomial. And to summarize, if we had this closed system of the heating, and we have an open system of the heating, we use delta U here, we use delta H here to capture the internal energy. And what we found was that assuming average or assuming T effect, the polynomial, or assuming average effect, or assuming 300 Kelvin, we got three different answers. And assuming this would be the baseline to say this is the most accurate, what we found is that by using an average delta U, it's about 1.6% off, but using this cold air standard, it's 12% off. And for the open system, it's 2.2% off, and then for this cold air standard, it's 16% off. So the assumptions you make matters, especially if it's such a big temperature change, which happens in real thermal systems, especially engines. Otto cycle for modeling a gasoline engine, diesel cycle modeling a diesel engine, Brayton cycle modeling a jet turbine cycle. We are going to apply the cold air standard assumption, which simplifies the analysis, but it gives us a relatively inaccurate result. Why do we do that? It's because we can still capture the fundamental physics and the theoretical limits with more simple equations, which are very useful to get a feel for this relationship and why this engine is designed how they are. these engines bring us to these high temperatures, but we still do this to simplify things because we're always starting at 300 Kelvin for many real applications, and we keep it there. To increase accuracy, we can capture some average in between to capture these two extreme cases, or we can do what NASA does and account for all of this using these polynomials in an equation. We can also use the tables to get the most accurate, and that's what this CP is fitted to, measured real results. But that's harder to do in a computational code to calculate these more efficiently for different cases. Okay, so that was our discussion on internal energy changes and temperature and heat capacities. Thanks, and I'll see you guys next time.